Okay, we're back in the second video now on Laplace transforms. This is covering the second section of the notes on Laplace transforms. And there's one more Laplace transform that we want to give, which is for a power, okay? The Laplace transform of t to the n. Okay, what would that be? This is actually quite a tricky one to do the integration for. And it's not unfeasibly difficult. It's integration by parts, but it has quite a few steps. This one is the number n factorial, and then we have s to the power n plus 1. Okay, and just as a reminder, what is a factorial? Okay, so the way this is described or defined is that we define 0 factorial to be equal to 1, okay, and then n factorial is equal to n times n minus 1 factorial. Okay, so that's a recursive definition. What does that really mean? Well, the honest way of thinking about this, the easy way to think about this is that if I have, say, 5 factorial, what is 5 factorial? 5 factorial would be 5 times 4 times 3 times 2 times 1. Okay, so 1 times 2 is 2, times 3 would be 6, times 4 would be 24, times 5 would be 120. Okay, and that's a number that most calculators are able to find. So for example, on my calculator here, if I hit 5, okay, my factorial symbol is the exclamation point, okay, and now I just need to find where that is. It's right up here. It's a second function of the inverse, so shift second function, I bring up the factorial, and that's 120. Okay, so that's the final Laplace transform that I need to share with you. Okay, and we now have a kind of a table of standard Laplace transforms. Okay. We have standard transforms. I'll give you an example of each one. Okay, so we'll call this side here is f of t. This side here will be fs. Okay, maybe I have to go a little bit further, but if we had a constant, we saw when we did our very first example, okay, which was here, okay, in the previous video, we saw that if we had A, the Laplace transform was A over S, okay, that was the simplest example. The next one that we would have is the Laplace transform for an exponential. So I would have e to the at, and that gave me 1 over s minus a. Okay, we would have the sine of a times t, which we saw, this was the case here. Okay, we had that one. So that was a over s squared plus a squared. We would have the cosine, which is very similar, but it's an s on top. Okay, s on top. And I have s squared plus a squared. continue that line a little bit longer. And finally, if I have t to the n, the one that was a little bit tricky and we decided we wouldn't do the proof of it, well then that was the one with the factorial n factorial over s to the n plus 1. Okay, and this standard list of transforms, you know, is like a table that I can make use of as a standard reference, and we'll talk about how to make use of this as a standard reference in just a moment. I'm just going to pause here for a second. Okay, so I paused there just for a moment just so I could organize my notes here, because I wanted to bring up this first page again, and I want you to look at this definition. Okay, this definition involves an integral. Okay, and we've spent a lot of time talking about integrals earlier in the semester. Okay, and the integrals that we're seeing here are maybe a little bit more difficult than some of the easier ones we looked at, but they're still integrals and they still follow the same rules that we discovered that we had for integrals. Okay, in particular, and this is very important, okay, if I have the Laplace transform for a sum, okay, so let's say I had the Laplace transform for f of t plus g of t. So I have two functions here, okay? Well then I would have f of t and g of t would be added together in here, which then I could do the multiplication out and I would have a sum of integrals. And we saw that a sum of integrals, we would have an integral of a sum, and we saw that the integral of a sum is the same as the sum of the integrals. So the Laplace transform of a sum is just the sum of the Laplace transforms, okay? So that would just be fs plus gs, okay? The Laplace transform of a sum is just the sum of the Laplace transforms, which is very nice. The other thing is that suppose instead of having a sum, suppose I had some constant multiplication. So I'm going to have k here, which is a constant, and say I wanted that Laplace transform. Well, then I would just have a constant of k buried in my integral, which I could just take outside, okay? So the constant would just come outside, and remember, the integral of a constant multiple is just that constant multiple of the integral. So this would just be k times fs, okay? And there is really nothing else that I need to worry about then, okay? These two rules here, this one and this one, are going to allow me to break down very complicated Laplace transforms into simpler parts using these standard transforms. So anytime I have a complicated expression, something that involves a sum or possibly a constant multiple of terms, well, that's really no difficulty. All I need to do is just use my table and these two rules here, and I'll be able to figure out what the answer is supposed to be. Okay? So let's do a couple of examples here. Okay? Let's say I take suppose I had the Laplace transform of this function. Suppose I want f of t to be 2 times the sine of 3t, okay, plus the cos of 3t. This is an example that's in the notes, okay? Well then, f of s is what? That's the Laplace transform of f of t, which is the Laplace transform of 2 times the sine of 3t plus the cosine of 3t. And we said that I was allowed to break this up, okay, and the way that I can break this up is that I can break up the sum and take out the constant multiple. So this is 2 times the Laplace transform for the sine of 3t, okay, plus the Laplace transform for the cosine of 3t. Okay, and that's all I need now to be able to consult my standard table here. Okay, so the Laplace transform for the sine of 3t, I get that from this one here. That's going to be sine of at, where a is 3. So I would find now from my table that I have 2 times 3 on top. I would have an s squared plus a 3 squared. And I would have cosine of at, where a was 3. So this term here is just going to be s on top. And I would have s squared plus 3 squared like that. Okay? And now it's pretty simple for me to finish this. Okay? How do I finish this? Well, I just multiply this 2 in, and we can see that I actually have a common denominator here. I have s squared plus 3 squared on the bottom of both. So what do I end up with? I end up with 6 from the first one. 2 times 3 is 6, plus s coming from the second one. On the bottom, I would have an s squared, and I would have a 3 squared, which is 9. Okay, so that's my answer. Like that. Okay. There's another one here which is a little bit more complicated, but it's fairly straightforward as well. It just uses a slightly different function. Okay, so we have f of t here, and this time we have t cubed plus 2 times t squared minus 4 times t plus the 1. Okay, so that means that f of s is the Laplace transform of ft. Okay, and now how do I get this? Well, this is equal to, I'm going to have the Laplace transform of t cubed, breaking up my sum and my taking out my constant multiples. I now have plus 2 times the Laplace transform of the t squared. I would have minus 4 times the Laplace transform of the t, and I would have the Laplace transform of the 1, like that. Okay? And of course now all I need is my table of standard transforms, and we can see that I'm dealing with powers in the first 3 cases, t cubed, t squared, t, and then I have a constant, and the constant is 1. So what do I have here? I have t cubed, so I have 3 factorial over s to the 3 plus 1, so it's 3 factorial. Coming from my table. Then I have 2 times, I have t squared here, so that means I'm going to have 2 factorial, and I'm going to have 2 plus 1 on the bottom as the power of s. Okay. Then I'm going to have minus 4 times, and we can see here that we have t, which is just t to the power 1, okay? So that's going to be 1 factorial, and I have t to the power 1 plus 1. And then finally, I have the Laplace transform of 1. 1 is just a constant, where a is 1, so this is just going to give me 1 over s. And now we can finish this example off, okay? Can finish this example off. It's very simple. We now have f of s is going to be equal to what? 3 factorial is 3 times 2 times 1. 3 times 2 times 1 is 6. So I have 6 on top. And I have 3 plus 1 on the bottom, so that's s to the 4. Okay. Then I have 2 times 2 factorial. 2 factorial is 2 times 1, which is 2. Multiply that by 2, I have 4. So I have plus 4 times on top. And I have s, and the power is 2 plus 1, which is, of course, 3. Okay. Then we see here I have minus 4. I have 1 factorial. 1 factorial is just 1. So this is minus 4 on top. On the bottom, I have the power t 1 plus 1, which is t, that should be s. My apologies. That should be s. That's s squared. And now I have 1 over s. Okay. Did I make a mistake? No, I didn't. So I just made the mistake there because I was hurrying. Okay. So whenever I have a Laplace transform, I can, more complicated one, I can break it up. Now the other thing I could do here is try to find a common denominator. We can see that I have s squared, s cubed, and s to the 4. So it's not difficult for me to find s to the 4 as being the common denominator. So that would mean I had 6. Then I would have 4 times s. I would have minus 4s squared. And I would have an s cubed. And I would have to take a common denominator here of s to the 4. Okay? And that would allow me to express that all as a single term. Okay. In the next video, I'm going to talk about something called the first shift theorems. And these tell us how to deal with some multiplications, okay? In particular, multiplications which involve exponential terms. Okay, thank you.